so it's for all alpha, there exists a gamma such that this is true. So these are somehow equivalent. Instead of solving for just minimizing this function with this penalty term, it's equivalent to minimizing this function but restricting that the norm of my A is less than something. Seems kind of strange, but how you see is if the alpha goes down, I have less penalty, the corresponding gamma goes up. So basically what you can think of doing is you solve for this alpha, you solve for this with an alpha, and then that A has some norm. That's exactly gamma. So there's always is this dual formulation. So I'm actually restricting that my slope is not too big. And so if you look at data like this, where it's all the way up here, really what I want to do is I want to restrict that my slope is not too big. I don't want a slope that's really vertical, because my error is measured in the vertical distance. That's really not saying too much. So I want to say my slope cannot be too vertical for some gamma bound on this. And again, I don't know what this gamma is. I can do cross-validation. It turns out this problem is easier to solve. So this problem, to solve for this A, so let's call this, so to solve for ridge regression, so this is going to be, instead of before I had px, py over squared, what I'm going to do instead is, I think this is alpha, let me just, either alpha or alpha squared. Yeah, so I just add in this denominator here, whatever the alpha is that I set in this function, I just divide through by adding this. And so in general, this is going to be equal to well, that's the identity matrix times X transpose. Right, so even in the higher dimensional form, in order to solve this, all I need to do is add this term inside the inverse. I just need to add this penalty, this alpha squared penalty. So solving for this, once I fix alpha, is as easy as solving the regular least squares. And this is going to keep, and it's equivalent to kind of keeping the slope to be not too big. Right, so what happens, the neat thing about this formulation is that if the slope I would have gotten out of the solution was already not going to be too large, then I would have gotten the same solution, right? If the optimal slope was here and this was within my threshold, it was within this threshold, then the solution won't have changed. It only changes when I have outliers which are too big. So that, this is usually always a good idea to do this ridge regression stuff. Now you need to go back and do, and we'll talk about cross-validation later, but you need to go back and do cross-validation to solve for what the value alpha is. But it's not too hard. And this will give you, in general, a more robust estimate. Okay, so there's something else which I'm going to preview now called the lasso. And it's, instead of doing the least squares, it's basically look like L1 alpha of PA, where I want to minimize A here. And this is going to be equal to the sum of Py minus A Px squared plus. Okay? So the only difference here is in the ridge regression, I had the 2 here. I squared A, the norm of A. Here, I don't square it. No, actually, I want to use, I don't want to do that. I want to actually take the L1 norm. Yeah, so I want to take the, I want to take this 1 norm here instead of the square 2 norm. And this is equal to the sum goes 1 to D of A. Okay, so this last looks very similar to the ridge regression. There's a similar dual thing here, except using that there's less than some gamma. So the 1 norm is less than some gamma. So it still has this property that if the slope is not too big, I'm going to get the same answer as before. But I'm using the L1 norm here instead. And so this is going to have, and we're going to spend a full lecture looking at this. It doesn't make so much, it makes no difference in 2 dimensions, because the 1 norm increases, the 2 norm of A also increases. So for every alpha I've chosen for the lasso, there's a similar alpha that will give me the exact same answer for the ridge regression. So in 2D, it doesn't make any difference, because I'm just looking at this value. And this is not squared and that's squared. This is the absolute value of this. But in higher dimensions, what this will do is it's actually going to have some of the coordinates of my coefficients be set to 0 if I optimize this. So this will get rid of some of these parameters that I don't need. Oh, shoot. So I'm out of time. So I want to mention one more thing. So, and kind of did here, that this vertical distance, if I instead map to the horizontal distance in red here, this is basically principal component analysis. And so we'll talk about this on Wednesday, and we'll talk about kind of how to think about this and how it's rotating in space and how to mention it. It's still minimizing the sum of the square distances here, but it's minimizing this projection. And you don't always want to do this. It seems like it should naturally be better, but there are very good reasons why you won't use PCA, and we'll talk about that on Wednesday.